boxes around some of this stuff. The first was this column we first analyzed, which was the x equals number of pips column. I want to draw a box around that first. That listing of values of x, okay, that x is called a random variable. Now, right now, it's somewhat boring because we're talking about the results of a die hitting the table. Somewhat boring. Later on, it's going to be the result of me asking an American, do you approve of how Congress is doing its job? Right now, Congress is less popular than syphilis. There's a higher infection rate for syphilis than there is a proportion of support for Congress. Just FYI. Still, it's gotten worse this last year. Just FYI.
Yeah.
But that is a die roll. It's a die roll. It's actually, what it is a coin flip. It's actually a coin flip. If I go and ask Gail, yes or no, is Congress doing a good job? Gail's going to say either yes or no.
Right.
But that doesn't mean the coin's 50-50. Her coin most likely isn't 50-50. It's slanted one way or the other. My job is to figure out via Gail and somebody else's vote how the American public feels about Congress. That's why you read Gallup polls. Dave?
Once you bring opinion into it, isn't it no longer random? Because they have a choice in
That's
how it
why
turns
the
out.
experimental design is so important. You try to rule the opinion out. Read those Gallup questions. When you guys gave me your Gallup results for your exams, those of you that did you actually go into the actual questionnaires that they used? They're fascinating. They try to remove the opinion and remove the bias from. I am asking Gail a very biased question because I'm trying to keep it simple and focus on the mathematics. There's way more than the math at work. You're correct, Dave, in saying that. But don't worry about that right now. I'm working on the framework versus the outer layer yet. We're getting there, I promise. Thank you. Lloyd, go.
Yeah, but on a random Gallup poll,
Yes.
don't they try to lead you with the question?
Good.
No?
Shh. That's a conspiracy theory. And we don't know who's watching this video. Let's leave all the... What you guys are asking are actually Math 246 questions. You're asking, okay, I get the mechanics. I understand the math of what's going on here. What I'm not following is, are we putting good numbers in? That's why I'm giving you dice and coins and cards and things like that. Because you can't argue rolling a die. Chances are gravity worked today when you threw the die on the ground, right?
Right.
You guys are asking way past that right now. And I want to keep coming back to that, but not right now. That's okay. Not to push it in the pipe. I'm pushing the pipe. Okay. Now that random variable, the most important part, I personally think, is the P of X column. You know how I'm always harping on you guys? Make sure when you run one var stat, you put L1, L2. If you forget L2, you're going to get a wrong. The reason it's so important is that column tells you how frequently or how infrequently something happens. So what these are the corresponding probabilities of the random variable x's. They're the corresponding probabilities of those random variables. Up till now, I've only called them frequencies, hence this little F column in here. But I want to move away from that because Gallup polls aren't based on frequency, they're based on probability. Why? We're getting to that too, I promise. That's all coming in time, and I promise to tie that all in. So notice how we did it two different ways, empirical and theoretical.
Right.
The reason I did it two different ways is twofold. Number one, let's talk about the empirical one first. The empirical one is important because this is how I'd say 99.99% of inferential statistics done in the world is done. You collect data and then form the ratios. So the pro to this way is that it's how this is how Nate Silver predicts elections, for example. It's how the 538 blog is run based on Excel simulations, for example. That's a pro. The con to it is what? And we saw a little bit of the con in our own data. What happens? What is the only thing we have to make sure we mention when we do that? Yes, we have to correct for any sampling error. There's going to be sampling error. We have to adjust that. But that's okay. We'll deal with that. That's measurable. So even though it's kind of a con, it really isn't, because we have a tool to deal with sampling error. As the samples get larger, that margin of error shrinks away anyway. We'll see an example of that momentarily. I've got some neat simulations to show you guys. The theoretical one. The theoretical one is pedagogically the best. Theoretical. Like when Tom told me 0.166 for the probabilities of the dice. The theoretical one, you know there is no margin of error. You know exactly what it's supposed to be, theoretically, right? There's no margin of error. No margin of error. Because you know exactly the answer. You flip a coin, it is 50-50. You roll a die, it is 1/6. You pull a card out of a deck, it's 1 in 4. There's no margin of error. Margin of error. What's the downside of theoretical probabilities?
It's not real.
Good. John, thank you. There are only 3 cases I can think of that they're applicable to. Cards, coins, and dice. Anything else, you have to make an assumption about the... I've made the joke, be careful crossing the street today. There is a 50% chance you're going to get hit. Why? Because you either do or you don't. That's a ridiculous argument, isn't it? There are only 2 outcomes when you cross the street, just like there are only 2 outcomes when I ask Gail, do you think Congress is doing a good job? But can we go straight from 2 outcomes to 2 equally likely outcomes? We can't make that assumption, can we? We shouldn't make that assumption anyway. You can, you just shouldn't. Now there are other random places where you can assume Ghostbusters. You know the movie Ghostbusters?
Yeah.
One of the first scenes in the movie is Bill Murray sitting in a lab with a cute grad student and a kind of a dorky grad student dude doing an ESP test on the dude and the girl. An ESP test is a 5-card test. It's 5 playing cards. Each has a different symbol on it. And the idea is the researcher holds the card up so the researcher can see it, but the subject can't, and says, use your ESP to tell me what's on this card. One of the cards is a star, one of them is like 3 wiggly lines. And the researchee then goes, it's a star. And then the researcher goes, check or minus. He either lets them know. Now, the Ghostbusters is funny because he shocks them every time they get it wrong, which is adorable. But the idea is, if you're guessing at what's on the card, how often are you going to get it right? 1 out of 5, 20% of the time. If there's 5 cards and you're guessing, you've got a 1 in 5 shot of getting it right. Just like,
You know what the choices are?
guess. You know there's 5 different shapes. Yes, you know what the choices are.
Oh, okay.
You don't know which one, just like you know what's on the die. You just don't know. Go.
4.
2, sorry. See, that's the thing. But there's a 1 in 6 chance, right, David?
There's only that 1 in 5 chance for you guess the same thing every time.
Careful, careful. I'm talking about on each trial, Dave. On each trial, you've got a 1 in 5 shot of hitting it. Just like here. Just like here. 1 in 6, 1 in 5. Fair? So there's very limited applications of this theoretical. So I like both. These are fun to deal with because we actually know the results. These are more realistic to deal with. And there is a link between them. I'm going to show you here in a second. Caitlin, you had a very important idea earlier. Whether it's empirical or theoretical, the sum of the probabilities is always 1 or 100%. That will always be true. That has to be true. That's how you know you've gotten what's called a probability distribution together. When you fuse this with this, when you fuse the x and the p of x column together into a t-table like this, what that's called is a probability distribution. And that's what I want to spend the rest of today and Thursday talking about, are those things. Probability distributions. Listing all the outcomes and their likelihoods side by side. Then we can find averages of them, we can find standard deviations, we can decide if we should use the average of the standard deviation. There's all kinds of questions we can ask at that point. But not yet. First thing I want to ask is, now that we know all these probabilities, and hopefully you guys have decided